For our research project, we are proposing to design and implement a prototype procedural animation system that incorporates feasible improvements upon current PA procedural animation algorithms in an attempt to improve current PA efficiency and improve humanoid locomotion on arbitrary uneven terrain while reducing the occasional environmental clipping of the humanoid limbs.
What is procedure animation? Procedure animation is a method of computer animation that is based on programmatic procedures and dynamic systems, rather than on data entered into a system beforehand. This means that procedure animation is real-time responsive and can handle a changing or unknown environment, rather than being built for one very particular sense. This makes it useful for animating physical processes such as cloth or smoke physics in film, or to get a baseline animation that can be further refined by an animator. In games, however, it is even more useful as the environment of a game is dynamic and animations need to be responsive to any game state. Human locomotion. Our focus is on human locomotion within procedure animation. In traditional computer animation, human characters are animated with keyframes, detailing the positions and rotations of particular body parts at particular times. Procedure animation extends or replaces this by using a dynamic system to refine or drive the placement and rotations of body parts. A common example is to use inverse kinematic on a keyframed animations to make feet place properly on uneven terrain. A more extreme example is where an entire character is animated via physical simulation.
Custom manipulators and controls make the character rigging and animation process for animators simpler and more efficient. Barty presented an automated rigging system specifically for quadruped characters, which is procedurally driven by requirements and principles set out by the animators themselves. Automating this process involved creating widgets based upon character properties such as height, proportions, and shape. These widgets were then replaced by joints, which were put over the base skeleton of the character. This enabled easy control and adjustment alongside far higher frame rates. Barty set out to propose a solution for manual rigging of quadruped characters, reason being manual rigging is extremely inefficient and repetitive, resulting in a decrease in overall character animation pipeline productivity due to the problematic nature of the manual rigging. The procedural technique can remedy this by automatically generating a character rig through a simple click. Barty's solution was a template-based procedural skeletal generator, which was not only far more efficient than manual rigging, it provided animators with a far more stress-free animation pipeline. The animation pipeline with custom manipulators. The proposed pipeline had two stages, the user intervention stage and the procedural creation stage. The first stage of the pipeline involved the creation of bipedal widgets, which were then adjusted and customized. Features that were adjusted include the size and positioning of each individual widget, such as the neck and spine widget. Once this first stage was completed, the second stage was left to the automatic rigging system to create each individual joint and link everything together to create one final quadruped rig. The resultant procedurally generated character rig combined the complex custom manipulators with simple and user-friendly functionality. In addition, each body part of the character rig offered isolation, where adding or deleting one body part did not affect any other part of the rig. The actual procedural creation of the quadruped involved the following in order: torso, head and neck, and finally legs. The process involved the use of inverse and forward kinematics. This automated procedural creation of the quadruped allowed for full functionality and scalability to be achieved efficiently, meaning the animator saved a vast amount of time by not having to manually create the character rig and only having to design specific character features and requirements. Automatic rigging as a whole. The automatic rigging system by Barty follows stringent rig and animation criteria. These included rig consistency, simpler controls for the animator, efficiency in terms of computational requirements and user interaction, adhesion to motion type, i.e. what setting and environment and attitude will the rig be used in, and no unexpected behavior from the animator's intention. The automatic rigging system was tested through creating countless rigs for a variety of different animal types and structures. The system was very flexible in adapting to different quadruped types with differing size and behavior. Each rig was fully independent in its body parts and had the ability to mirror either side, left or right of itself. Due to the same underlying structure of each rig, full transferability of poses from one rig to another was made possible. The rigs were also particularly efficient due to its design being based around only needing a limited number of joints, whilst maximizing range of movement and customizability, resulting in real-time interaction of the rig for the animator. Example-based motion synthesis. The focus of Feng Shui and Shapiro was to enable the natural movement of virtual characters while simultaneously avoiding obstacles and being able to interact with random objects within a virtual environment. As the priority of virtual character simulation has shifted to individual properties such as direct interaction between individual characters and dynamic objects, object manipulation has become ever increasingly important. Rather than focusing on broad interaction, attention has been shifted to fine movements such as hand positioning and postures. However, this brings about challenges such as ensuring there is no unnecessary penetration between the virtual character's limbs and the objects. Enabling this would require an extremely accurate locomotion system and a precise object manipulation structure to deal with the unexpected changes in the object/environment positioning. Feng Shui and Shapiro presented a virtual character model which involved techniques from a variety of areas such as locomotion, object manipulation, gaze, and pathfinding. By incorporating example-based locomotion, Feng Shui and Shapiro were able to provide natural character movement at sufficient speeds for many real-time applications. While many other systems at the time were focused on object manipulation in a static environment, Feng Shui and Shapiro developed a means of touching, reaching, and grasping in a dynamic environment. With no prior knowledge of the environment such as the placement or location of objects, the virtual characters were able to adapt in real time to environmental changes by constantly adjusting their bodies through previous examples of locomotion. The system structure of example-based motion synthesis. The system developed by Feng Shui and Shapiro had a hierarchical controller structure. This enabled the state of a character to be adjusted by such controllers, where the output of one controller would be input to the next controller in line. The hierarchy meant that higher controllers had increased priority than the lowest ones, meaning the higher controllers could choose to change or disregard the previous state. The order of the controller stack for each evaluation phase consisted of world offset, idle motion, locomotion, animation, reach, grab, gaze, and finally constraint. The first 4 controllers guided the virtual character to a specific object. The next 2, reach and grab, generate the motion of the arms, hands, and fingers towards the object. Gaze provided head and eye motion, and lastly, the constraint controller made sure that no user or target constraints were violated during the whole character movement process, and conflicts between each controller did not arise. Although full body motion was achieved through inverse kinematics, individual body part motion was based mostly on example motion data parametrized through motion data blending, which were then combined with inverse kinematics where example motions did not exist. Depending on the previous example motions, the resultant animation would have slight variations in areas such as smoothness and speed. However, due to constant parameter tuning, example-based motion would be highly beneficial for pathfinding and generate very realistic human motion. Overall, motion blending and inverse kinematics allowed for accurate movement that still maintained a natural aesthetic on the character. Feng Shui and Shapiro experimented by placing a character in the center of multiple objects, where the character was then able to navigate and reach for objects with its whole body. While navigating, the character was able to evade arbitrary obstacles in a realistic human manner with full body rigidity maintained. Under time conditions, Feng Shui and Shapiro found that the system was able to perform each evaluation update on the controller stack in less than 2 milliseconds, and was able to handle many characters simultaneously, moving and manipulating objects while sacrificing very little frame rate as the number of characters increased.
Bhatti et al. 2016 paper looked into 3D procedural animation using trigonometric expressions. The problem to develop physics-based kinematics or dynamic motion models to generate complex human motion is still a challenging problem. However, using geometric, trigonometric, sine and cosine functions, we can then procedurally generate rigged character skeletons. Motion equations are applied on each body part individually to generate periodic motion for each gait. In particular, sine function. The nature of sine functions allow motion frequencies to be controlled with different amplitudes and phases of motion curve. A natural biped skeleton or biped skeletal joint trajectories follow simple sinusoidal patterns, using the sine function to generate motion curves with oscillating phases. The diagram below shows a walk cycle of a biped character, which follows the simple sinusoidal pattern. To generate the procedural motion of a biped character, the skeletal rig is segregated into 5 main sections: pelvic and spine expression, chest oscillation in forward and backward directions, shoulder oscillations, shoulder and arm swinging expressions, legs and feet expressions. As you can see in all the expressions listed above, they have all integrated sine or cosine function, which suggests the biped character follows a simple sinusoidal pattern. Bhatti et al. 2016 paper also included a simple use of GUI interface. It was created to have simple sliders for the users to manipulate the parameters of the motion equations. Users can modify the biped motion behavior individually at real time as the motion is generated using expressions inside the Maya application, which we mentioned earlier. Producing a wider range of animations which can be easily customized and further extended according to the requirement of the scene. Below is an overview of the procedural animation system.
First, AI-friendly procedure animation system, Twink. The system designs a simplified dynamic simulation specifically that provides easy control to the user. For example, the character is using linear force in Cartesian coordinates to control, as is modeling by particulars and rows. Furthermore, it is easy to control independently for different parts of the character by the application of external force. It provides a series of capabilities that including gold direct character locomotion, object manipulation, and physical interactions between characters, such as huging and dragging. On the other hand, no matter what the other part of the character is doing, the puppet control style allows one part of a character is controlled through a single set of gains. For instance, the stable conditions while the postured controlled and locking system during different load conditions. Especially the system does not need to retain, while characters gesturing, carrying objects or holding on to another characters. Twink shows how well-designed code points for controlled and simulations can simplify motion synthesis, so that very simple techniques are sufficient. Although it is not compatible with all applications, it is very suitable for interpretation and narration with cartoon credibility but the scalability. Support for character interactions and the interface of higher-level AI components are particularly important.
This lecture comes from the 2014 Game Developers Conference Animation Bootcamp section. Rosen's lecture is great because it goes through his methods for animating his game as a sole programmer and animator. With a set of only 13 keyframes and a lot of well-thought-out procedures, he was able to achieve a great degree of readability and lifelikeness in his character. Rosen began by placing his idle-posed character on top of his character's colliders that respond to input and prevent clipping. This character is made to face its direction of velocity and tilt from its feet towards the direction of acceleration. This was influenced by his observation that a person must lean into acceleration to maintain their center of mass being below and supported by their feet at all times. He made 2 keyframes for running. He used a wheel that rotated with movement to sync the run cycle with movement. He also added a walk cycle, and the 2 animations are interpolated between for intermediary speeds. A crouch using a spring damper equation was also added. It had good easing and follow-through and was strong enough to be used as a landing pose for jumping. To refine the animations, IK, inverse kinematics, was used to find positions that kept the hands and feet outside of world geometry and to adjust the joints in the limbs to naturally place them there. A ledge climbing animation was implemented mostly using IK. Additionally, IK was used to give head and torso look targets. This made the character seem more alive and aware of its surroundings. Few keyframes and a high degree of procedurality allowed Rosen to create a wide breadth of dynamic and responsive animations without an animator on staff. Nonlinear interpolations and transitions are used extensively in Rosen's work to easily achieve far more natural-looking animations. IK was used to prevent clipping, but it seems that where it was not used, clipping did occur more often. Rosen only spoke of 2-bone IK, which is not a necessary limitation. However, Rosen also discussed the limitations of IK, and how too much use of it is like animating inside a text editor. We identified research gaps that came up across multiple papers. These were mainly that animations often do not look lifelike or are inaccurate, high-speed movements can look especially strange, and difficulties around using IK. Naturally, different papers had different strengths and weaknesses, so not all gaps were present in each system. We have listed the gaps here with the authors of the papers where these gaps were noticeable. We are most concerned with the first 3 gaps listed. and those are what we'll be working to address. We believe that they are interconnected, and when addressed together should reinforce each other's solutions. Because IK is so involved in preventing clipping, it is important to work with it properly, but it has difficulties and drawbacks, so considering it while working towards more lifelike animations will help alleviate the drawbacks, with both sides leading to a stronger outcome.
Now we'll talk about our project proposal. The main aim of our project proposal is to find improved methods of procedural locomotion to reduce its unwanted environmental collisions and increase its accuracy. The aim can be split up into 3 questions. 1. What causes unwanted collisions and terrain clipping? Maybe there's a fault within the code, or possibly the parameters could be tweaked in order to fix this. 2. How can collisions be better modeled without reducing performance too much to allow for real-time processing? At what point are there diminishing returns? 3. How could motion paths that are more accurate to real-life motion be generated? Our objectives can be split up into 3 categories: research, analysis, and development. During the research portion, we aim to identify weaknesses in existing models that allow clipping to occur. In the analysis phase, we consider improvements or new methods that could better prevent collisions, as well as estimate and analyze performance of new improved accuracy methods. Then we aim to develop our own algorithm by studying film reference for how people navigate uneven environments, as well as derive new motion paths and curves that more accurately follow real motion.
For our timeline, we have divided the timeline by tasks. First, we are going to find and process existing procedural animation techniques, compare and contrast these techniques, perform analysis on computational complexity, theorize limitations on these procedural animation techniques and possible solutions. After that, we'll build our prototypes and theorize the solution, evaluate our prototype performance, organize the prototypes, information and results, and finally, we will write the report. For team roles and responsibilities, we have divided the team mostly into 2 parts, into development and analysis. John, Roland, Chloe, and Luke will focus more on the prototype's development. And for I will be in charge of the PA algorithm analysis and comparison and evaluation. However, all the members are going to work on the theorized limitations and solutions, overlooking the project progress, organization of results and outcome, and report writing.
Our initial methodology was to have a theoretical basis to analyze existing algorithms, identify limitations, then theorize new solutions by developing prototypes to improve previous algorithms. We then expanded it into more concrete steps, where we 1. Look at a wide array of techniques for procedural locomotion. 2. Theorize limitations in existing techniques and perform analysis on computational complexity. Identifying limitations gives us a good way to find solutions to these limitations. Complexity analysis will make sure that everything can run in real time. 3. Theorize solutions to existing problems and make sure they work in real time. 4. Build prototypes of the most promising theories. We'll implement the original procedural animation system and a version with our proposed solution to compare. We'll do this in the Unity game engine since it is a powerful 3D engine and we'll have experience with it on the team. 5. Evaluate prototypes against initially researched algorithms. Determine whether our theories improve the efficiency and realism of procedural animation.